Hey, how you doing, guys? Do a little bit of op amps here. This is a question from a Circuits 2 exam. Um, Basically, a couple things you'll learn, or some things you need to know going into it, is characteristics of an ideal op amp. Some characteristics of an ideal op amp are VP and VN are equal to each other, which is VP is this node here on the positive terminal, and VN is this node here on the negative terminal. IP equals IN equals 0. There's no current going through here. There's absolutely no current going into this. That's just the characteristic of an ideal op amp, and it'll help you figure out the equations for these guys. The impedance of a capacitor is 1 over S. Some of you might have seen it as 1 over J omega C, but they're equivalent. Zeros and poles are something you'll get to know. It's something you already know. It's basically when does your equation equal 0, and when does your equation in the denominator equal 0. So this is basically for your numerator, when your numerator equals 0, and this is for when your denominator equals 0. And node voltage, something I always, node voltage or KCL, or however you want it, those are synonymous. But basically, I always do tail minus the head over impedance. And if you'll see what I mean when I do the node voltage this way, it's kind of like a vector. You know, the tail of your vector minus the head of your vector, and you always know which way your current's going. And this, I just always do them like that, and I haven't failed me yet. I know a lot of people can get confused with how to do the node voltage and which way the current's going and this and that, but if you follow this, it doesn't. You'll get it right every time. So basically, here is our op amp. The question states to find H of S, find the zeros and the poles. If you're unfamiliar with H of S is basically a transfer function from the frequency domain that we could take the Laplace transform of and find in the time domain. Basically, in circuits, we like to look at things a couple different ways, and one of those ways is in the time domain, which is f of t, and then in the frequency domain, which is it could be H of S or big F of S, and a lot of times these capitals. The capital here is for in the frequency domain. So let's get started here. Look at this op amp. The first thing we need to do, which I already stated earlier, was some characteristics of an ideal op amp. More specifically, right now, what I need to focus on is the VP. VP and VN equal each other. Notice that there's no resistance or impedance in this path here, and it goes straight to ground. And ground is at a 0 voltage, so basically their VP equals 0. Okay, so VP equals VN equals 0. So I use that to form a node equation right here at VN, because I need to relate VG with V out. So I take VN, I say Vn minus Vg all over this impedance. Now notice we have a capacitor here. I need to change that into the frequency domain. I need to change it into impedance. And what I'm just going to do, instead of using numbers, because everything gets hairy when you start using numbers, go figure, it's math. But what I'll just do is use some variables, and I'll just keep it at SC, and I'll put SC1 here because we have another capacitor right here, and this one I'm going to put 1 over SC2. All right, I could just plug the numbers in, but we could use these, and it might be easier. I certainly think it is. So we have 1,000 plus 1 over SC1. Our next one is going to be next portion, so we went that way. Now we basically have to follow all these nodes here in node voltage, and if you know about the nodes, basically this is just one big node here. This can collapse, and this can collapse here. So I'm just going to follow all the paths that connect here to form my node voltage equation. So I'm going to go this way. So I get V in minus V out over 40,000. And next, I'm going to go up through this capacitor 2, which is going to be plus, and V in minus V out over my impedance. My impedance is 1 over SC2, 1 over SC2, and this all equals 0 because that's what Kirchhoff's current law is. All currents going in and out of one node must equal 0, and that's what we got. So basically now we need to simplify this, and the H of S equation is in the form of H of S equals V out over VG. So we need to form this equation, and you can see we have V out and VG here. And simply we'll go back to this fact, and all these equal 0. 0, 0, 0. That makes things really easy. And so let's form another, our simplify it a little bit here. We have VG minus VG over 1,000 plus 1 over SC1. Okay, plus minus, we'll do a minus there, minus V out over 40,000 plus, minus again, sorry, minus V out over 1 over SC2 equals 0. And I want to get, I'm just going to pull out my VG and my V out to help me get it in the form I want. Minus 1 over 1,000 plus 1 over SC1. And this portion, I need to change colors, it's getting crazy. Pull out this minus and a V out. And then that's going to be 1 minus 40,000. And if you notice, this just flips all the way up there. So that's where I get this S2, and that's going to be all over 40,000 because I need to make the denominator the same to add fractions, right? So we'll go down just a little bit further, and this does equal 0. Change colors. So I'm simply going to move both of these over, move this all the way over. So when I do that, actually this becomes an equal sign. Now we need to get V out. I need to get VG under V out. In order to do that, I'm going to pull this over here and multiply, and then I'm going to pull this over here. Alright, so we end up with V out over VG equals -1 over 1,000 plus 1 over SC1. Boom, boom. The reciprocal, take the reciprocal here of that, which is, we know the reciprocal, 1 minus 40,000 S times that. Okay. Just a little legwork here. Multiply this over, switch it up, multiply this over, get a negative 40,000 all over So we'll leave these just like this. We're going to leave these in their, we'll call them factored form. We still need to simplify them just a little bit. Plus 1 over SC1, 1 minus 40,000 SC2. Okay, and basically I want to get S down here all by itself in a factored fashion, all by itself, in it, something we're used to seeing. In order to do that, let's look at this part right here first. How can I get this S up here and all by itself? So in order for me to do that, I need to multiply by S over 1,000 over S over 1,000. Okay, so this is going to multiply to the top, and this is going to multiply to this bottom here, and S will be all by itself in this part. Now, if I look at the next part here, how can I get this S all by itself? In order for me to do that, I need to do something similar. 40,000 C2 all over 1 over 40,000. Now this might look a little crazy, but it's just, it really would be something you would do in multiple steps. I'm just consolidating these steps here, and it's just simple algebra. It's just multiplying by 1. This whole thing is equal to 1. This whole thing is equal to 1, and it's just changing these into a form that we wanted. That's actually helpful for us. So after doing so, after carrying that out, we end up with minus S over 1,000 C2 all over S plus 1 over 1,000 C1. This is 1 over 40,000 C2 and plus S. So this is where we need to resort back and plug in for our C's. And C1 was equal to, I think, 200 nanofarads, which is farads as a unit of capacitance. And C2 was 25 farads, I believe. And so when we plug those in and crunch the numbers in a calculator here, which I have done to save some time already, your H of S will equal V out over VG, which equals minus 40,000 S all over S plus, 5,000 and S plus 1,000. And at this point, to find our poles and zeros, it's quite elementary. You can just see that our 0 equals 0, because remember, it's the denominator. That equals 0, it equals 0. Our poles is when this is 0 and this is 0. So the poles equal negative 5,000 and negative 1,000. All right, great, guys. Thanks for watching. Remember to subscribe, comment, like. Let me know how you like the videos. Appreciate it.